Hello, everyone. Okay, we'll just have a few more coming in, and we'll close the door. Excellent. So we'll now kickstart the next talk. Let me first, before we begin, allow me to introduce Mr. Peter Silberman. Peter Silberman is an engineer.
Thank you.
Before he even presents, wow, that's a vote of confidence there. He's an engineer from Mandiant Inc. He works at Mandiant as an engineer on the agent team, and for a number of years now, Peter has specialized in offensive and defensive kernel technologies, reverse engineering, and vulnerability discovery. He enjoys automating solutions to problems both in the domain of reverse engineering and rootkit analysis. Peter now spends most of his time researching solutions to memory forensics problems. Peter is the co-author and teacher of Advanced Memory Forensics in Incident Response. And although he is college educated, Peter does not believe formal education should interfere with learning. Today he's going to be presenting full process reconstitution from memory, and do join me in welcoming Mr. Peter Silberman.
Thank you. Thank you. All right, so as she said, I'm just going to rehash things because my slides are set up that way. I'm here to talk to you today about full process reconstitution from memory. What that means, well, first, what I'm going to do is I'm going to tell you a little about myself, cover a couple things real quick, won't bore you. Then I'm going to talk to you about acquiring physical memory, because before we can do full process reconstitution, we need access to physical memory, and we'll discuss the different methods there. We'll do a little deep diving on the software physical memory acquisition. We'll then talk about traditional process acquisition, what that means, what we define it as, what you may think of it as. We'll discuss some of the pros and cons with regard to that. Then we'll go to the new process acquisition approach, the one that we'll be releasing here at Hack in the Box, the one that will be included in the tool, and the one that we'll continue to talk about throughout the slides. Once we talk about process acquisition, you guys have a good understanding of it. We're going to talk to you about some of the really advanced things we can do after we've acquired a full process. Once we've done that, that would be the find executable code bullet you see there. Then we're going to talk to you about Memorize, which is the free tool that we're releasing here at Hack in the Box. I couldn't travel across the world with 300 CDs. It really was pretty unfeasible. So there are cards. I have cards with the URL. They're in front, so grab them at any point so you guys can download the tool. And hopefully I can get about 20 minutes of demoing just different things in, since I think that would be the most fun. So who am I? Real quick, we already covered what I do. I've co-written 2 projects, RAID, which stands for Rootkit Analysis, Identification, and Elimination. And I'm also co-author of FU2, the second version of FU. I contribute to Uninformed Journal, and I do security research on the side. So before we get going, we got to talk about our stated goal. What is full process reconstitution? It's sort of a new term that we sort of coined here. Basically, it's when you acquire a process, you don't want just the executable. You want to dump all the executables from memory. That's the DLLs the process has loaded, the executable in the process address space, and on top of that, you want process-centric information. So I'm going to want the stacks for the threads that are executing. I'm going to want the heap information. I want that all on disk so I can look at it and use it how I might please in either malware analysis or memory forensics. So that's what full process reconstitution is. All right, so what is required? Well, there are a couple things that are required. We need access to physical memory. We either need access via live physical access, or we need a memory dump that was created, and we can treat that as physical memory. After we have access to physical memory, either via a memory dump or live physical memory, I need the ability to find all the processes on a system, whether they're hidden or unhidden. Once we've found every process, that means we can find the process that we want to acquire from. Once we can do that, we need to be able to parse that process's memory sections. And we'll talk about what parsing memory sections means and what it is in a couple more slides. So that's what's required for full process reconstitution. So there are 2 different ways to acquire physical memory. The first genre, if you will, is hardware physical memory acquisition. And that's going to be your PCI and your FireWire. PCI, Joe Grand of Grand Idea Studios came up with a hardware device called Tribble. It's a PCI card. You stick it in. It'll suck the physical memory off the machine, store it for later analysis. The second method, FireWire, was developed by a couple people. The first group was a CanSec West 05. They gave a presentation. their method wasn't as solid as they would have liked. They were only really able to acquire physical memory off of XP Service Pack 2, I believe. The second guy is Adam Boulot, who did I think I'm pronouncing his last name right. I may not be. He did a paper called Hit by a Bus. And basically, he was able to trick Windows into thinking his laptop was an iPod device. And he was able to suck physical memory off of the computer he connected to via FireWire. And so those are the two host-based physical memory acquisition, or two hardware-based physical memory acquisition techniques that can be used. But what we're concerned about and what we'll be discussing here today is the software method. So we want to acquire physical memory via software. And to do this, we're going to open a handle to the device physical memory. Device physical memory is a section object that's been exposed by Windows to allow access to physical memory. And this is how we can get live access to physical memory. Next, we're going to want to read from this handle that we've gotten to read physical memory. But we don't know where we're reading. So what we have to do is we take the virtual address that we want to read from. We're going to do a translation, because we need to translate that virtual address to a physical address and then seek within this section object to that location and then read the physical memory that corresponds with that virtual address. So I know that's a lot to digest. So basically, virtual addresses, we parse them in two ways. If the system has page addressing extension enabled, which is PAE for short, we're going to parse the first 2 bits of the virtual address. That's going to represent the page directory page table. The next 9 is going to be the page directory entry. The 9 after that is going to be the page table entry. And then the last 12 is going to be the physical offset in memory. And we do this, and then we seek around in the section object to get to the location of physical memory where this virtual address's buffer is stored. If page PAE is disabled, we're going to go about it a little differently. The first 10 bits are going to be the page directory entry. The next 10 are going to be the page table entry. And the last 12 is going to be the physical offset in memory. So it's just 2 different ways. Basically, Memorize, the tool, acts as its own MMU to translate virtual addresses, and that's how we're able to use utilizing paging file and things like that. So we've translated the virtual address to a corresponding physical memory page, and we've mapped that page into our own buffer that we now control. We have 2 options once we've done that. The first, if we're in live memory analysis mode where we're like scanning for processes, we want to dump the handles a process has, we want to do something in live memory, we're going to scan that buffer for certain signatures or certain characteristics that we're looking for depending on what has been enabled and what has been asked of us by the user. If we're being asked to write the physical memory, if we're being asked to essentially say, create a memory dump, put it on disk, and we'll use it later, we'll just write this page to disk and keep reading in a loop. So those are the 2 different types of what we may do with the buffer once we have it. One caveat that we have to address is that user mode access is not allowed at the beginning, is not allowed to this section object from Windows 2000 Service Pack 1 and on. So we can't, in user mode, open a handle to this section object, which creates a problem because we pride ourselves on being able to support Windows 2000 to Windows 2000 Service Pack 4 to Windows 2003. So we had to come up with a way around this. And this is true in Vista as well. So our solution, I'm going to actually use an animation here since those are more fun. What we do is we run our tool Memorize. Once we've run it, Memorize will install a driver. This driver is now in kernel mode, running in ring 0, so it has permissions to open this section object. Memorize is going to request a handle to device physical memory from the driver. So the driver is going to open this device up in kernel land. Once it's opened the device up, open the device getting a handle back, it's going to pass that handle back to user land. So we now have the handle that we couldn't get in user land using a driver. It's a technique that's being used by a couple other tools we'll talk to you about in a second. So once we have this handle in user land, we can now read physical memory in user land, which is our goal. So let's say Memorize wants to read the virtual address you see on the screen. What would happen is Memorize would translate that virtual address to the physical address, read that buffer from device physical memory, store the buffer, and we're going to say for this instance that we are actually in memory dumping mode. So we're going to write that buffer to disk. Once we've done that, we loop, and that's how we create a memory dump. We don't repeat the process of requesting the handle. Once we have the handle, we do that once. So the translation is what occurs in the loop. So that's how Memorize does memory acquisition. We are not unique in this aspect. There's 3 other freely available tools out there. MDD is open source, and Win32DD are both open source memory acquisition tools. They only do memory acquisition. A quick note, Win32DD was written by Matt Suchet. He is, if any of you are familiar with the hibernation file, he wrote the Sandman project. So that's a good website to have in mind. He does a lot of cool stuff in Python with parsing things. So that's a good place to go. And then we also do it. But Memorize, which stands for Memory and Analyze put together, does it a little differently. Win32DD and MDD rely on system calls. System calls can be subverted. As we all know, rootkits from way back when can subvert system calls. The system calls that Win32 and MDD rely on are MDD relies on global memory status EX, and Win32DD relies on ZW query system information. Both of these calls, what they'll end up doing is returning the actual physical size of memory that these programs should create. The subversion can occur where you can hook these API calls and return a smaller physical memory size set. And what that means is that you're able to say, don't acquire up here. My driver may be in this location. I don't really want you up this way. So I'm just going to give you a smaller set. If memory should be 512, let's divide it in half and say 256 is the actual physical memory size. This is a theoretical rootkit approach. As far as I know, it's not been implemented, but it wouldn't be hard. One thing we'll say is that the API calls that MDD and Win32DD call are not really unique. Or actually, I apologize, they are unique, that they're not called by many processes. Memorize does not rely on these API calls. What Memorize does is it relies upon an API call that is very common to us, map view of file. Most of us should know about it. It's used by most processes. Most applications will have this call somewhere. It's just a common way to read a file. We only use this to determine the size of physical memory because we'll actually get an error once we read past the end. So we don't need to predetermine the physical memory size. Map view of file, we are aware, can be subverted. How an attacker would go about doing this is they would have to know their driver's physical address, where their driver is in physical memory. So they'd have to take the virtual addresses that their drivers are on, translate that to physical memory, and then block reads to that physical memory. We believe that's a lot harder to do, 1, because they'd have to implement their own translation, which is not easy, and 2, because physical memory is not contiguous. So an attacker may make the mistake of saying, well, I got the first virtual address, I got the first physical memory page I'm on, I'm just going to add to that and say that my driver is going to be here. Well, we know that virtual addresses don't map to contiguous physical memory pages, so that makes it that much harder. So we try to minimize the possible subversion. So that's some of the software drawbacks. So let's talk about traditional process acquisition, because basically what we're saying is that we're coming up with a new approach. So what is the traditional approach that we're trying to avoid? And the traditional approach is not a bad approach. It serves a lot of purposes. I still use it personally, even with the ability to do new process acquisition. This is essentially, the old approach is acquiring an executable from memory. And why you want to do this is basically you have a file on disk. Let's say it's packed with UPX, which is pretty common. It doesn't look nice on disk. It doesn't look nice in IDA just because it's packed. But we know it's going to completely unpack itself in memory. So doing a traditional process acquisition is going to give us a view of the file that we don't have on disk and make our lives as a reverse engineer or a malware analyst a lot easier. We're going to see strings we didn't see before. We may see API calls we didn't see before. It's just a nice view. And we also know that if it's in memory, that's what's actually executing. So that's a good thing to think about. You don't know what it's doing on disk, but if it's in memory, you get a snapshot of it. You know what it's doing. The traditional process acquisition that we'll refer to from here on out really is going to be an ollie debug type process acquisition where we use ollie dump just to attach. Ollie dump does a lot of really cool stuff that we're going to talk about in a second. All right. So there are many pros to traditional process acquisition. The biggest and best pro that we really find makes traditional process acquisition useful and stay around is that ollie dump and other tools out there will perform the section and import address table fix-ups for you. They automate that. They build the IAT. It's a beautiful thing. It's very nice. It helps with analysis later on. We don't do that. Memorize will not fix anything up for you. And we'll explain why and give you some real-world examples of why we don't do that and what you can miss by doing actual fix-ups. But there are some cons to traditional process acquisition, which is sort of what led us to be where we are right now.